So let's see. Hope you can see the screen. You can see my screen. Yeah. So today is on single value decomposition. I think we have hinted on it a few times, couple of times. So you might have heard about it, but I don't know how last week's class went, but I'm sure you delved into the intricacies of the composition of matrices and all of that. So when I say decomposition, you understand it's just sort of breaking down the matrices into simpler forms, right? So you could work with the matrix in a different structure. You could compress it, you could approximate it, you could even scale it up. And these are all algorithms, are all methods that are used in machine learning, in data processing, and all of that to restructure your data so that you can work with them. You could use it to reduce the size of your data. You could while keeping important features. You could you could scale up, shrink data, so you could delve deeper into it if you want like some details in whatever data you're working in. So there are different decomposition techniques, and I think we'll touch on a couple of them. I think SVD. I don't know if we've done principal component analysis PCA, but that's also another decomposition technique. But let's see where this notebook takes us in the SVD, delve into SVD, and then whatever we come across, we'll just discuss that a little. Okay. So the first the first thing we did, I think, was to import the libraries to be using. I'm sure we are familiar with all of these libraries: NumPy, Matplotlib library, SciPy, because we'll be calling whatever we are doing. I'm not going to be doing the program. I'm going to write the algorithm from scratch. So we'll be calling it from the SciPy linear algebra library. And this is what we'll be using the LU, which I think the last 2 weeks I touched on that, the lower and upper triangles, LU. And we have Matplotlib library for our plots. And these parameters, just to make sure that the values that we get from our numpys are set to 4 decimal places. That's what this position over here is doing, setting our number of decimal places to 4, so that when we are printing all floats, unless you override it in whatever code you are writing, unless you specify that you want this particular number of decimal places, everything will be to 4 decimal places. And we also suppress this so that it prevents NumPy from using those scientific notation for small numbers, if you have maybe 0.000 something, it's going to be 1 e exponent negative 0.5. So instead of the scientific notation for very, very small numbers, we want to print them like 0.000 so that we can understand how small the numbers are. I mean, all of these you can't do without them, but then just to make just so that the values are sort of uniformed. And we have this one over here too for the for all the plots we're printing. This is a default figure size for all the plots, unless of course it's specified in the code, then we'll not use that. But then yeah, so just explaining the libraries that we have right here. Okay, I hope it's moving. Yes. Okay, so matrix decomposition, as I was explaining, breaking down complex matrix into simpler components, like factoring the number 10. You can break it down to 2 times 5, and it's a simpler form of this, right? So we're just breaking now into simpler components. That's also why it reveals hidden structure of whatever matrix that you have. It also makes the computation faster, and it enables you to do some compression and approximation of your matches, right? So quickly, let's review LU and QL, right? So these are two very important matrix decompositions, the LU decomposition and the QL decomposition. And I'm sure you've missed them already. LU, and L stands for the lower and U stands for upper. But this is the technique that divides your matrix into lower triangles and upper triangles. Okay. And what we are doing, we first defined our 2 by 2 matrix over here in A, right? Define that 2 by 2 matrix, and then we use the LU function from the linear algebra library, the scipy.linear algebra library, to perform the LU decomposition. So we split it to P, L, and U, right? P is the permutation matrix. We might not directly use this for the verification here, but it's usually part of the LU decomposition just to ensure the numerical stability and all that. But the main thing we are interested in is in the L, the lower and the upper triangular matrix, right? So the lower triangular matrix, all the elements that's just above the main diagonal line, and U are the upper triangular matrix, that's all the elements below the main diagonal, the all elements above the main diagonal, that's the upper triangular matrix and all that. So we go on to do the print it. So right, so running the trying to get the LU values, right? All you have to do is this block of line. So we can call our P, L, and U. We don't use the P value, so usually we just print out the L and the U values. As you can see over here, we just printed the L and the U values. So you pass your matrix in. Then this is our matrix A that has been defined over here. So we pass it into the function, and then these are the the parameters, or the values that we can get after we do after we compute the LU decomposition. Okay, so we printed the L and the U values and separated it with a line, a new line, and did the verification using the performing the L by U matrix multiplication. Right. So as you can see, this is our L, our lower matrix, where all the elements above the main diagonal are equal to 0, and our lower matrix, and sorry, in our upper triangular matrix, where all the elements all the elements below the main diagonal are 0, as you can see. So this is the diagonal, the 6 and 1 is the diagonal, and all the elements that falls below it are 0. That's the upper triangular. And same for this, where the elements above the diagonal 1 1 is equals to 0. So when you multiply this and this using matrix multiplication, you get back your original. So you see the original was 6 3 and 4 3, as you can see over here. So we get back the original, and do same for so this is then there's another method, that's the Cura decomposition, which that's also available in the linear algebra library. All you have to do is change the LU to Cura and specify the parameters that you'll be calling out. Okay, so as you can see, this one was just LU, and we didn't have to include the linear algebra.lu because we had called it specifically over here. So we can just call it from this, right? But for the Cura, we didn't do that. So we started with this and picked Cura directly from the original scipy.linear algebra, as you can see over here, right? So linear algebra.ql, right? Yeah, so pass your matrix over here and then you get that. So it's also what does that? When you multiply, the Q is the orthogonal, right?
Hello.
Yeah, yeah, hello.
Sorry, but please, what is the P doing? What is the meaning of the P in the lower upper
The
decomposition? The
the
P,
permutation matrix.
the permutation matrix. Okay.
Yeah, yeah. It's for we are not going to use it in the to prove to do the verification. It's usually there to ensure that it's to handle certain specific matrix properties. If you want to do something specifically, then you call it. But what we wanted to do was just to break this into lower and upper, and then sort of bring it back together and see whether we get the original. So even if you realize,
Mm,
because we didn't include the P and we did just the L and U, the position of this swapped. So it's supposed to be 4-3 and 6-3, but it became 6-3 and 4-3. Right? It's sort of interchanged. But with the P in play and included in the verification, you get something that will be more closer to the original. So it's just like
okay.
to ensure numerical stability, but it, the when we designed this notebook, they didn't include that in the like in the calculation. But then you can choose to overlook that and just focus on the L and U because that was what we're trying to prove. That's what we're trying to use for the proving. Okay. Okay. So it's usually parts, but over here we are not using it just so we keep everything basic and easy to understand. Okay. So yeah, same for the LU. We just change the function and then pass in our matrix, and we get the Q, which is the orthogonal, and the R is the upper triangular, right? So upper triangular R, which is here is minus 7.2 and so on so on. So, but you can see all the values below the diagonal is 0. If it's a 3 by 3, you would understand better, but then 2 by 2. So this is the diagonal and everything under it is 0. And the orthogonal is also Q, which is displayed Y. So when you find the matrix, when you multiply Q and R, you get the original matrix for point 3 and 6.3. So just like the analogy over here, like factoring 10 to be 2 and 5, that's what that's what decomposition is all about. You break it down into simpler elements that you can manipulate in different ways while you are still maintaining the data in the image. Just that you can work with them in different spaces or different ways. Sometimes you have to transpose them much another, and you get stuff. You get it to be maybe in a 3D space. Maybe initially it was a 2D matrix, but when you transpose it, you become a 3D matrix, and now you can manipulate it in the third dimension and all of that, but still the same data. Okay. So let's go on to talk about the yeah. So for yeah, so let's talk about the singular value decomposition matrix. This is also saying it's a factorization technique, right? A matrix factorization technique that will help you decompose a matrix into three simpler matrices, right? We have the U, which is the left singular vectors, the left singular vectors, and we have the summation over here, this which is the singular values you get. They will be stored over here in a 1D matrix, and the V and MV, right, which is the right singular vectors, but transposed over here. Okay. So A is our input data matrix and usually represents your data sets where perhaps the rows could be maybe the samples, whether they are images, documents, or users or whatever. And the columns will be the features, the in data set terms, maybe like pixel values or the word frequencies or item ratings. And in our example, A is a 2 by 3 matrix over here. Right? A is a 2 by 3 matrix, meaning two samples with maybe three features each, or the other way around. Doesn't matter. And we have US, or S is summation. I'm calling it, the summation is also singular value, so I'm calling S. Right, so U, S, and fit C, where U is the left singular vectors, usually a 2 by 2 matrix in this case, because our input is going to be, our input is a 2 by 3 matrix. This will be a 2 by 2 matrix because yeah, so it's an orthogonal, right? It's an orthogonal matrix when the columns are the left singular vectors. These vectors span the row space of A, and you can think of them as representing the principal components or maybe the latent factors of your samples or observations. So the relationship between your data points in a new lower dimensional space. That's what it captures. It captures the relationship between your data points in a lower dimensional space. And the S, that's the singular values, which is usually a 1D array because you just have you just have them like as individual points, or no, not points, yeah, so just values, individual values. So they are, it's just usually a 1D. It could be two, three values, it could be 150, it could be plenty. So depending on the number of singular values you have, you can retain more information, or you can choose you can choose the number of information you want. So perhaps if you have an image with maybe 400 singular values, when you're doing the singular value decomposition, you could choose to retain, say, 100 singular values, and maybe the first 100 singular values, and that will contain almost enough information for you to use. So it's just the singular values which are always non-negative, and they are arranged from the largest to the smallest. And the largest obviously contains more information as compared to the smallest. So usually the values at the tail end, if you have 400 singular values, the 400th value won't have so much information. So that's the whole logic of the singular value decomposition. This is the whole foundation of it. You break your matrix into three different matrices, and the one in the middle, that's the singular values, has that's what allows you to scale or shrink your data set or your matrix. So depending on the number of singular values you have, you could choose to keep a few of them just to work with and drop the rest. And you still have enough information, right? So you can check for the error margin, the the how what's the word? How close it is to the original in terms of the values you've retained, and then you can be adjusting the value to get something that's in you, what you want. So yeah, so we'll get to that. Get to that. Right. So the singular values represent the strength or importance of each corresponding singular vector. Larger values also indicates directions or features along which the data varies the most. Right, and these values are very important for dimensionality reduction. So by keeping only the largest singular values and their corresponding vectors, you retain most of the information in the data. Right, and then the transposed V matrix, which is the also stands for the right singular vectors, right? It's also an orthogonal matrix. In this case, it's 3 by 3, and it's the the rows are the right singular. So in this vectors, the columns, they span the column space of A, right? So the left one works with expands the row values m, as you can see, so m by m, and the right one spans the column values n, just n by n transposed. Okay, and that's what makes it a 3 by 3 matrix. Yeah, that's what makes it 3 by 3 matrix, because this is a 2 by 3, so n by n is 3 by 3. Right. So geometric meaning over here, orthogonals. When you hear orthogonals, it's just rotating, right? And so this is rotating. This is stretching it, or compressing it, compressing or stretching. So scaling, and this is also rotating. Okay. So yeah, SVD. So this is the mathematical foundation for PCA, right? Principal component analysis. And usually, when you keep the top k singular values and their corresponding u and v vectors, you can create a low rank approximation of the original matrix A, and this will reduce the number of features, as I was saying, while retaining most of the variance. And it is very important for reducing noise. Maybe you want to visualize something, or even speed up how fast algorithms run. You can reduce the number of features but still retain the information. You are doing maybe feature extraction. You can use the singular vectors as v, right, to even capture patterns in your data. This you see in when you're doing unsupervised feature learning and all that. You can do noise reduction and image compression and all of that with SVD. I think there's the image compression that we will try out to see. Right, so over here we are just trying to trying to do the SVD computation, right? So we have our matrix over here. This is checking the shape of the matrix, which I was saying is a 2 by 3 matrix. And then we use the SVD function in linear algebra, right? So linear algebra.svd to, I think in Colab, it's even that's the explanation for you and all of that. So the linear algebra library in SVD to compute the U, which is the left singular vectors, S the singular values, and VT, which is the right singular vectors. Okay, so we print them out and we check the shape, right? So as I was saying, it's a 2 by 3. This is a 2 by 2 because it's the row m, right? So m by m, and yeah, so this automatically does a computation for you, and you get to see all of the values over here. For larger data sets, you won't be able to visualize it because a lot of numbers, lots of numbers. So you won't be able to visualize this. However, you can probably check the shape and all that, but you won't be able to visualize the singular basis. But like this is what's happening in there. Right, so we have u and we have our singular values. We have two of them, from the highest 3 and the lowest 1, right? And so 1D, right? 1D, and we have right singular vectors over here too, so 3 by 3. Right, so we're going to reconstruct our matrix A from the decomposition we done, the SVD decomposition we done over here. Right, so that's what we did. We have our sigma which is an empty matrix with the same dimensions as the original. So 2 by 3, right? It's an empty matrix. It's going to hold the singular values, right? And go on to specify the singular values s, which was a 1D array. So we place it along the main diagonals of our matrix sigma, right? So this is it. So we place it along the diagonals of our matrix sigma, and because it's a non-square, the NP does that creates a square diagonal matrix and then embeds it into the larger sigma matrix, and then we'll fill the rest with zeros. Okay, so once we do this, and then we create a new variable a reconstructed, which multiplies the three SVD components back together. So the left singular vectors times the sigma, which is a matrix containing our singular values, right? And the transpose, the right singular vectors transposed. All right, so mathematically, that's the definition of SVD, right? So A is equal to U times the sigma times the V transpose. And we print it, right? Print it, and we check the margin of error. Okay. And as you can, so this is the reconstructed A. This is our original 1 minus 2, 0, 0 minus 2, 1. And as you can see, it's being reconstructed as 1 minus 2, 0, minus 0, minus 2, 1. The only difference you can see is the minus 0, which is also, it's not even, it's negligible because minus 0 is minus 0. 0 is non-negative already. So, guys, you check the error over here. This is actually 0.00000 to the 16 places before 4 comes, right? So it's this times 10 is prime minus 16, which is very small, almost negligible. I mean, it's actually negligible, but very small. And just to get value, I mean, but you get the idea. It's the margin of error is very small. So yeah, so that's this is how you can reconstruct even an image, right? An image from SVD. After you break it down to SVD, that's how you can do the reconstruction, right? And you get very similar. It gets very similar to the original. Okay, right. So when you use all the singular values you have, the SVD will provide a perfect, exact decomposition of the original matrix. So you realize we had two singular values, which is 3 and 1, and we used all of that in recreating the reconstructing the original. So it's very close to the original, right? And this is like the foundation, right? This is the real ML that often happens when you perform low rank approximation and all that. So when you but when you intentionally discard the smaller singular values and their corresponding vectors to achieve maybe some reduction in your dimensional compression, in those cases, either you reconstructed the matrix that you are going to reconstruct will be an approximation, and the error will also not be zero but still very small enough to retain the useful information in whatever the original matrix was. Right. Hello, can you hear me? Can you see my screen? All right. Okay, so I think I was talking about the reconstruction of A from the SVD, right? From the SVD decomposition. And the fact that when you use all the singular values, you get a perfect or almost perfect reconstruction of the matrix A. But when you just pick some and drop some, you get something very similar. It depends on the the number of k values, number of single values. Stephen, kindly mute yourself. Yeah, yeah. So, hello, Stephen. Please mute yourself. Yeah. I'm not able to
Okay.
mute you. Can you mute yourself for me? Yeah. Okay. Thank you. So, yeah. So when you pick some of the singular values as I was explaining, you get something that's closer to the original, but I mean, depending on the values you pick and depending on how many of the values you pick, you get something that's close on it. We'll see how that looks when we get to the image compression parts. All right, so over here was just visualizing what happens when you're doing the SVD, right? So this is our original inputs circle on my left side. In the 2D space, it looks like this is a perfect circle, right? But once you perform the SVD decomposition on it and you plot and you this is what the matrix look like. It rotates and then scales up again. So as you can see, first it was spanning from -1 to 1, right? So yeah, it was -1 to 1, like 2, right? But over here it's spanning from somewhere -2.5 to 2.5. So it's rotated and it's stretched and it's flipped. It's rotated once more. So it looks more like an ellipse now, but then it's still the original image that has just been perhaps how do I put it? Has just been restructured or broken down into something else for you to be able to work with. But it's still the original image, right? So the eigenvalues, so the singular values are 3.6, which is the blue. So as I said earlier, some of the singular values, the maximum singular values can contain direction. So and yeah, so we have 3 and 1, right? That's still 2D, but it looks like it's in a 3D space, but it's still 2D. So if you visualize it where the from the z-axis or where this line is pointing, it will look like a circle once more, right? Yeah. So one application of SVD is in image compression, right? Treats the images as matrix, and then you apply the SVD to it. This is something that is been that is used a lot when you are trying to maybe you have a data set that's very how do I put it? It's very large, right? And you want to work with it, but you have the processing capability to work with that. You can reduce, you can shrink it, you can compress it using SVD, and you retain up to a percentage of the image that's at your own discretion. Looking for something that's optimum, something that will work fine on your system and also gets enough information from it. And then you throw the remaining that you don't want away and both work with the compress the compressed form of the image, right? So here I'm going to load a simple grayscale image and compute the SVD using the equation that we use, the left singular left the u times the summation times the vt, right? And we also approximate by keeping only the top singular values, which we'll define as k, and then we'll visualize the original and the compressed and compute the error and also the compression ratio. All right. So same libraries that we're using, the only new ones, okay, a couple of new ones. So we have pill. Pill allows you to handle, this is to work with images, right? So pill stands for pillow, PILLOW. So pillow library is used to handle image files, and we have requests to also download files from any URL you have. So if you, because we are not going to import the file into the notebook as a data set, we're going to rather download it from a site. We use the request so that I can access the URL and download. And when we download it, we have to store it somewhere, right? To store the data before we read it with Pillow. And that's what the bytes IO is doing, right? So it just keeps the downloaded image over here before we read it with the Pillow library, right? So it's pretty straightforward what we've imported over here. So NumPy as usual and Matplots library for our plots. Okay. Okay. Right. So I think everything is all right. So this is the URL of the image that I'll be using from Unsplash, and this line, this response is storing the request function, the get URL function, which is going to download the image right from the URL, and then over here we store the downloaded image over here, right? So image just open using the bytes IO to store the contents over here from the request function. Right, so that's what we're doing. So all what we're doing over here is just to download the image and store it in this variable. And now anytime I want to call the image, we just call this variable. Okay, so we did so this is conversion to grayscale over here, using the pillow that converts. And yeah, so the L mode in pillow stands for luminance, luminance, right, lights, and it's going to create a sort of 8-bit pixel image with the intensity ranging from 0 to 255, 256, 255. Yeah, so it's between 0 to 255. So it's going to be from 0 to 255. And SVD is typically applied to grayscale images because the color image will require you to pre-process the image in 3 separate color channels, right? RGB, that's if it's RGB. If it's a different, if it's in a different image format that's not RGB, you have to also process in that number of channels, which makes it more complex. That's why we are converting to grayscale, so that it's just one value for a channel, right? And it will be easier over there, right? Okay. And next thing over here we are doing is computing. Okay, let me explain over here. So the image and the full matrix that is set to false. It's all parts of preparing the. Okay, so that's in the computing the SVD aspect. So I think we understand up to this point because we did it with the matrix, right? we had our matrix and we just did this and passing the matrix over here. But this time we are passing the image file. That's the only difference, right? The image that has been converted to grayscale, we convert it, we pass it over here and convert it. Sorry, we pass it into the matrix and we set the full matrix to false, which will tell NumPy to return sort of the economical or the budget form of SVD, which means that the U will have the same number of columns as there are in the singular values, which is the minimum value of the original vector, right? And VT will also have the same number of rows, which is more memory efficient. If you have a larger data set, it will delay the time that's going to use for the reconstruction. So just setting this to false allows it to use the matrix in the economical form. It doesn't use everything. All right, and yeah, so that's why that's the just to reduce the computational power, right, making it more memory efficient when m or n is much larger than the other, and often sufficient for applications like compression, right? So as you all know, U for left singular vectors, S for the singular values, which is a 1D array, sorted in descending order, of course, and the V transpose is the matrix of the right singular vectors. Okay, so we go on to the reconstruction, which is just multiplying them together, multiplying U, S, and VT, right? So U times S times V transpose, just as we did with the matrix, right? So we set K to be 50. K is just a variable that's going to determine how many of the largest singular values and their corresponding singular vectors are we going to retain for reconstruction. Okay, so as I was saying, you can retain everything, you can set it to a number, because actual compression, we are doing compression because we don't want to work with everything. So this value is what's doing the work for us. We are going to limit it to the first 50 singular values, and you know that they are arranged in descending order from the highest to the lowest. So the first 50 and the highest contains the highest being the value that contains most of the energy, most of the information, right? So the first 50 is the first 50 large values, the first 50 large singular values that contains the information in the image, right? So we retain that, and then and that's what we use. So we retain that number of singular values, and we use the corresponding singular vectors, the corresponding left singular vectors, and the corresponding right singular vectors. So that's what we're doing. So the first one is selecting the first 50 columns of the U matrix. So this is row, this is column. So first 50 columns. And the second one is doing the first 50 rows of the VT matrix, right? Rows and columns. So first 50. And this is creating a diagonal matrix, right? Using the first 50 singular values from the S array. So it's going to create a diagonal matrix and just filling the diagonals with the first 50 columns of array. Sorry, the first 50 values from the S array, and then we do the matrix multiplication of the three of them. So it's just the same thing we did for the matrix, but this time our K is getting a value. We are not using everything. In the previous matrix, we used everything, and you could see that what we got was very similar to the original. So this time we're not using everything. And then we go ahead and do the plotting. So we plot the original image and the compressed image. So the original image is IMG, and the compressed image is approx, right? That's what's stored here as approx. And we turn the color maps over here to gray. So it knows to work with grayscale image. If you don't do that, Matplotlib library will automatically give intensity values for grayscale images because it imagines that the other channels like have values and it itself fills in those values. So you get a grayscale image when you plot it. So we just set the color maps to gray so that it doesn't give us like it doesn't let me just show you what I mean. Let me just have to run everything, also I get an error. All right, so you see, even though we're using a grayscale image, because the color maps is not mapped to grayscale, the math plus library is automatically filling in the other channels with values, with intensity values, but we want all of that to be zero. So we set the color map to gray. Okay, it's just something that's when you're working with images, you face a lot. Right. That was not what the original image looks like, actually. Let me see if I can follow the link to show you the original image, but I'm positive that's not what it looks like. Oh, another time. So yeah, so this is the original image. As you can see, it's sharper than the sorry. As you can see, it's sharper than the compressed one, right? And even though we are retaining just the first 50, we still get something that's close enough to this, close enough to the original. So k is equal to 50. Let's see what happens when we increase the k value, so maybe 150. Yeah, so it takes the time, and you can see it's a more clearer image, right? Because now we are working with more singular values, but all of these just makes the computation longer. I mean, it's still not as sharp as the original, but it's very close and you won't even notice the difference. But ideally, this is actually compressed and this is not. Let's see when we increase to maybe 400, we get. So be taking note of the relative error as well. I'll go back to the 50 and we'll compare and see the relative error. Right, so you can see over here, this is the compressed when k is equals to the first 400 singular values. It's actually almost the same, and you realize here the relative error is zero, compression ratio 1.6, which the compression ratio is just yeah. So the compression ratio is just the original, the original image requires some values to store, and the compressed image also requires some values to store. So when you sum these values, the ratio tells you what fraction of the original data you are retaining. So the compression ratio is just the the value of the original data we are retaining, and you can see we're even retaining more than 100% of it, right? It should be one, which tells so okay. So our singular values were 400, so we are retaining like everything, and as you can see, the relative error is lower. So let's, because we want to compress, let's take it back to 50 and see the value of the relative error value over here. Right, so you can see the error value is even also very close to zero, about 9.96%, right? 0.0, which is like 10% error. And you can even see it, right? You can see the difference over here. And the compression ratio is no more one, it's 0.2. It's like we are retaining 20% of the original image over here, right? So that's what the singular value decomposition is all about. Breaking your image into your data set into three components. The middle one, that's the singular values, is that's the magic. The When you retain the singular values, it comes with its left and right singular vectors. So the number of singular values you retain will come with its what's the word? It comes with its accompanying left and right vectors, and multiplying these values together reconstructs your original image. So the more you pick, the the what's the word? The more informed, the more closer it is to the original. The less you pick, the less closer it is to the original. So you have to find the balance, get something that you want to that like sounds good for what you have, right? I hope up to this point it's clear. Yeah, I hope it's clear. Alright, so we have this the connection between singular value decomposition and eigen decomposition. So also one of the foundations in linear algebra and machine learning. And the idea is to just understand how SVD relates to PCA. All right, so let's. All right, so from the lecture slides, I'm guessing you missed these equations where you just interchanging the transpose, the multiplication. So when you transpose the original A, you multiply it by the transpose of A, you get the U values. You get something different. And when you multiply it the other way around as well, you get something different, right? And yeah, so over here we have 2 by 3 matrix A, which is the same thing we have been using throughout, right? And this is going to be our data sets to demonstrate the relationship. First is to compute A transpose times A. So transpose the original matrix and we multiply it by itself, right? So that's ATA over here. And doing the transpose is just A dot T, right? A dot T. And matrix multiply itself by A. We print the output over here, and yeah, so this is the A transpose times A. This is the value. This is the value of the matrix over here. You get a 3 by 3 matrix. And also do the eigen decomposition. Alright, so the eigen comma eigenvex, this first line. And yeah, so this first line computes the eigen decomposition of the ATA matrix, right? This ATA matrix, and returns eigenvalues and eigenvectors of the matrix. And the eigenvalues are just they are 1D arrays, and the eigenvectors are the matrix where each column is an eigenvector corresponding to an eigenvalue. And then what the second one is doing, the second line is just going to sort the eigenvalues, because when you generate them, they are not really in any order. So we sort them into the descending order as from the highest to the lowest, which allows us to, because the singular values that we are going to compare them to are ordered from the highest to the lowest, right? The original singular value, when you do a singular value decomposition, automatically they are ordered from highest to lowest. So we just sort it over here so that we can be able to compare it well. I mean, for this one, I'm just going to get two values, but for larger data sets, you get multiple eigen values and you get multiple singular values. So just sort them so we can sort of compare it line by line, sort of, right? And then we print the values over here, and yeah, we print the values over here, and we also print the square roots of the singular values as well. And then we do same for the SVD. SVD, this is what we do, but we're not interested in the U and the VT, just the S. So we print just the S values over here, and yeah, this is just a conditional statement to print this if the eigenvalues and S are equal, right? And it should print it. If the square roots, then it should print it for us. So as you can see, the square roots of the eigenvalues are that's what gives you the singular values. So these are eigenvalues 9, 1, and -0. So we find the square roots of that and we get 3 and 1, which is the same as the singular values 3 and 1. Right. And then yeah, so that's the relationship between the eigenvalues and singular values, relationship between eigen decomposition and singular value decomposition. The square roots of the eigenvalues are the same as the singular values you get from doing SVD. Okay, and this is just another extra line to demonstrate the relationship between the eigenvalues and the and SVD, right? So just as we did in the previous cell, we computed the A transpose A. This time we're going to do A times A transpose, just switching the positions and see what we also get over here, right? And it's the same, almost the same thing we are doing. This time we are going to compute only the eigenvalues of the A times A transpose matrix. And yeah, so this is a different, instead of the linear algebra dot, how did we calculate it? So we use linear algebra dot eig, right? We give us the eigenvalues and the eigenvectors and all that. As for this one, we are using linear algebra dot eigenvals, which is going to give us just the eigenvalues. Okay, just the eigenvalues of the A times A transpose matrix, right? So that's what we need for the verification, just the values. And again, we source them. Again, we source them in descending order over here. So sourcing it in the np.sorts, right? Sorting it, whatever we get here, in descending order. And then we go ahead to print the eigenvalues, and yeah, we set a conditional. I mean, just the same thing we did in the previous one. So as you can see, 9 and 1, which that's the eigenvalues, right? Which matches the same 9 and 1 we had over here, right? So you find the square root of 9 and 1, you get 3 and 1, which is the values of the that's the singular values, right? So A times A transpose is fundamentally the same as A transpose times A, even though you get different matrices. So you see A by A times A transpose, we got a 2 by 2 matrix, 5, 4, and 4, 5. But when we did A transpose times A, we got a 3 by 3 matrix. But still, the eigenvalues are the same, right? Shows that matrix, you can manipulate it in so many ways, but the data, the information is in it is still the same, right? The time. Okay. So the next thing is the okay. Next thing is the low rank approximation. Yes, okay. 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 So the next thing is the low rank approximation. Right. I think after that we have just a few. Yeah. Okay. So this is more or more or less another practical application of SVD for the low rank approximation. Just demonstrates how the singular values contribute to the information content of a matrix, which I've sort of said all over and over again, how the singular values contribute to the amount of information of a matrix, right? So for data compression and maybe some PCA, this is very important, right? Low rank approximation. So let's talk about the code. We have np dot random dot seed 42, which which just generates random numbers for us, right? And the ensures that the numbers that are generated are sort of reproducible. So if you run this code multiple times, you get the same random matrix, sort of, just so that when I run everything again, I don't get entirely different outputs over here. So that's what the np.random.seed is doing for us, just ensuring that the random numbers that are generated can be reproduced again when I run the cell again. Okay, and we go on to create a 5 by 5 matrix with the random numbers that are drawn, right? So the random numbers that we get over here, we create a 5 by 5 matrix with it using just a random normal distribution of it. and then we work with that. So A equals A times A transpose is just allows us to create a orthogonal or maybe a symmetric positive semi-definite matrix. So we are guaranteed that the matrix will have real non-negative eigenvalues, and are often used as, and this is like often used as examples in linear algebra. So we wanted to create a random matrix, so we just generated random numbers, random numbers, and populated a 5 by 5 matrix with these numbers. And we multiplied the 5 by 5 matrix by the transpose of itself to get a matrix that we are sure that we will get eigenvalues that are not negative, right? So essentially, that's what I'm doing, just creating a random 5 by 5 matrix that will not give us errors when we are working with. Okay, and then we go ahead and run this, or do this to compute the SVD values for us, to help us with the SVD. Okay, I think with you for this one you understand, and we are just going to print only the singular values, the S. Don't need the U and the VT for now, just the S values. And then we go ahead to approximate for different ranks. So we do we set up this function that will just that will do the approximation for different k values, different ranks. So we start with 1, 2, 3, and 5, just to demonstrate how much information we get when we use when we alter our k values. That's why I did that in the image. So when you change the value of k, you get something that's more depending on the value you use. So if you use a value, if you select all the eigenvalues, you get something that's it's more similar to k. I mean, this is a 5 by 5 matrix, and the number of singular values were 5. Okay, so we start from using one singular value, then we do 2, then do 3, and we compare the number of the percentage of information that we retain. So that's what we are trying to do, right? And this is the low rank appropriation formula. It is a low rank appropriation formula where it reconstructs A only using the first k values and their corresponding singular vectors, right? This is what we did in the image compression that we're doing, right? Yeah, the compression that we did. So it's going to loop through, it's going to take k is equals to 1 and run it through, calculate the percentage error, and and also computes the percentage of energy that is being retained, and also computes the percentage error for us. And this is the formula to calculate the percentage error. All right. Using the Frobenius norm, we subtract the this what do I even call this? This is the reconstructed matrix. So we subtract the reconstructed matrix from the original and divide it by the Frobenius norm of the original and multiply by 100 to get the percentage of energy retained, right? And we subtract that from 100 to get the percentage error, right? So that's what we are trying to do by here. And if you see For k equals to 1, we retain 60% of the information and 40% margin of error. We do same for k equals 70, k equals 2, we get 76% of the information. And when k equals 5, that's all the singular values, we retain 100% of the information and there is no percentage of error, there's no margin of error. All right, so that's what's going on. That's what the low rank operation is all about, right? Just trying to understand what happens when you select you select the lower singular values, right? And that's, you can work with 80%, 88% of the image, but then that will be just the first three, what do you call it, the first three singular values, which is almost enough information at a lesser, at a compressed form of the original data set, right? Which will be almost similar to the original. I mean, it's almost 90%. All right, so that's something. Yeah. And go ahead to visualize the energy distribution. So this plot, the singular value spectrum, just shows each singular value as a bar, right? So we have 5 singular values. So it just shows as a bar, and the values are, as you are aware, they are arranged, they are sorted in descending order, so from the highest to the lowest. And you can quickly see how their magnitudes are dropping off, right? From 13 to 4 point something, almost 5, and then to 2.5, sort of, and then we have 1 point something, and we have 0 point something, almost 0. And a sharp drop indicates that a large portion of the matrix information is concentrated in a few components. So with the first spectrum, when you plot a spectrum for an image, perhaps you see a very sharp drop from one singular value. So you know that most of the information are concentrated in the first singular value. So if I pick the first singular value to work with, even though it might not look clear to you, it's still almost all that it shows you that almost all the information is concentrated over here, and you can get more, you can work with it as if it's the original at a very compressed format, right? And yeah, that's essentially, yeah, just to understand how the values, the the values relate with each other, right? And there's the energy capture plots, which also shows you the percentage, the cumulative energy, right? The cumulative percentage of the total energy captured as you include more singular values. So as you include more singular values, we did 1, we did 2, we did 3, we did 4, and we did 5. All right, 1, 2, 3, 4, 5, right? Yeah. So shows you how the cumulative percentage of the total energy changes as you include more singular values, right? So it's just like calculating the running sum square square singular values. I think we did that over here in the code, the cumulative sum over here, right? So the square singular, we square the singular values. Anytime you see this is squared, right? Double asterisk is squared. And then we know that these values are vice proportional to variance, and we divide that by the total sum of the singular value squared and multiply it by 100 to get the cumulative percentage. So this plot is just useful for choosing the k by setting a threshold. So maybe we set a threshold that we want to retain maybe 90% of our information. We know that we can work with just k values, maybe around 1.5. We can retain 90% of our email of the information, right? Because the first value contains almost all the information, and the rest are just between 94 to 100, so just 6% of the information, right? So all of these are just to help you determine the key value to use whenever you're working. Because what you might see with your eye might just be biased to you, but then if you plot the actual data, you visualize what you have, you get something more reliable to work with, right? So yeah, that's just how we have here the value spectrum and the energy capture. I think someone's mic is on. Oh, it's from the class. Let me leave that. I'm getting some. I don't know where it's from. I think Steven, please can you mute yourself? I'm hearing